We've already talked about some of the general ways that electromagnetic radiation interacts with matter, and now we're going to explore some of our UV and visible light a little bit more in detail in terms of the kinds of interactions that they have with matter. So we said that the UV and visible wavelengths do two things mainly. They excite electrons in atoms or molecules, and they break bonds. And what we haven't really talked about is that both of these two effects, one of the most important things that they do is that they increase the chances that a chemical reaction will occur. So in case one, where we've excited electrons make our particle have a higher energy itself in general. And so if a particle has a higher energy, if you remember from chemical kinetics discussions of how chemical reactions occur, one of the importances is that we have to have enough energy to overcome a reaction barrier. So the higher energy particle is maybe more likely to overcome any kind of activation energy barrier that we have. So the second one of these breaking bonds is that if we break bonds, we also create reactive particles that again might be higher energy. And we might be breaking up parts of the molecule that otherwise wouldn't be reactive. So one of these is radicals. And just as a quick reminder, a radical is an atom that has, or a molecule fragment that has one or more unpaired electrons. So a chlorine radical, remember that chlorine has 7 valence electrons, and so if it is not in its ion form, normally we see chloride, which then has 8 valence electrons, right? But if we aren't in that form, if we have a chlorine radical, it is a neutral atom that happens to be highly reactive because it has this unpaired electron right over here. Okay, we also have oxygen radicals available. So those ones we would probably draw like this. And then there's lots and lots of different molecules as well. Nitric oxide is one. Actually, I think I have to do the Lewis dot structure for this one, right? We've got 11 electrons, so if we use 2 as a bond, we're going to need probably 3, right? 2, 4, 6, 7, 8, 9. Nope, too many. Two, 4, 6, 8, 10, 11. All right, so we've got our nitric oxide, and you can see that it also has an unpaired electron over here, and that makes it highly reactive. We'll talk about nitric oxide and other oxides a lot later on, but I just generally wanted to remind you that if we have electromagnetic radiation as an energy source, then this allows all kinds of opportunities in terms of forming excited or higher energy species, and then we can write a reaction that looks a bit like this. We can say we've got some reactants, we add energy, we're going to write H nu, and we make some products. You might also see this as like sometimes people will draw a little line, sometimes they'll put a little gamma here. These all mean that we are using electromagnetic radiation to get this reaction going. Now, this reaction and all photolysis reactions, all light-based, that's what photolysis means. So photo meaning light, lysis meaning breaking. All photolysis reactions are first-order reactions. And this first order is a kinetic term that tells us how these chemicals react. And if you need a little review on chemical kinetics, I'm going to record a separate video on it and put it in our fundamental skills section. Kinetics is one of those areas that a lot of people struggle with, so don't be shy about reviewing it or about asking additional questions. Okay, so anyway, I'm going to go through some of the basics here. For our first order reaction, the reaction rate for a first order reaction is going to look like a rate constant and then whatever our first order reactant concentration is. So our reactant will be reacting at a first order. That's what the first order is about, that it's just depends on the concentration of their reaction and also on this rate constant. So if we think about the units of this reaction, it's always a good idea. Rate is almost always in units like molarity per second. Sometimes we have a little bit of variety here, but this reactant is also therefore going to be in molarity units, which means that our rate constant is going to have 1/seconds. And if this reminds you of frequency, that's exactly what it is. Right? This rate constant is a frequency that relates to how often a chemical reaction is going to take place. So this, for these photolysis reactions, we're going to do K sub P. So this is our photolysis rate constant. And it's possible to calculate these photolysis constants. And the equation in our book looks pretty intimidating, but we're going to go ahead and work it out. It's not as bad as it looks. Okay, so I'm going to go ahead and write it out. It is the integral over the appropriate wavelengths. And then we have 3 parts. All of these functions, this is 3 different functions I'm going to explain in a second. They all depend on the wavelength, and then we would look at the change in wavelengths, and so we would add them up, and that's what the integral is about. And so we can approximate this by just taking a summation over all appropriate wavelengths and just taking these functions and summing them together. And that will give us a good enough estimate. Okay, so we would have all 3 parts and add them up. And we'll go through an example here so you can see it. But first, I'm going to talk about these 3 parts of our function. Okay, 1, 2, and 3. So 1, this is the Greek letter phi. You might also hear it phi. So 2 Greek letters, phi and lambda, phi and lambda. This is the quantum yield. It's a fancy name. And the quantum yield is a fancy name for just saying if a photon hits a molecule, how many times does that actually cause a reaction? So what fraction of photons hitting molecules results in a reaction? So if we think about that, if every photon produced a reaction, that would be a 100% hit rate, right? In that case, then phi of lambda would equal 1 for whatever that particular wavelength was. And if no reactions ever occurred, then our quantum yield is 0. And this is our functional range. We have a maximum of each photon produces a reaction in the molecule. This is exceedingly rare. And then we also have a situation where no photon ever causes a reaction, which is often possible. Okay, so our units for the phi of lambda are in molecules per photon. Okay, so our second piece, A of lambda, if you look in the environmental chemistry book, you'll see that this is really just the absorptivity constant, the molar absorptivity. It has a little bit of different units, but it's really just the molar absorptivity from Beer's law. So I used an epsilon in the lecture, but the environmental chemistry book uses an A, so this is good because it reminds us that the molar absorptivity does depend on the wavelength, which is a good idea. So this is in units of centimeters squared per molecule, and in this form it is called the absorption cross-section. So A is for absorption. And you can think about it as a target. How big of a target does the molecule make, right? So that's where the cross-section point comes in. So depending on our molecule's shape and orientation and size, it's going to have a different cross-section. And depending on that molecule, it will have a certain area that it presents for the light to be able to hit it, okay? And then our third factor, I was going to say actually, just real quick, that in our Beer's law, when I had epsilon, I had units of 1 over molar centimeters. And this A is in centimeters squared per molecule. And it might be worth a couple of minutes of your time to do a unit conversion from one of these to the other, because you can. It's just a straight unit conversion, but you might play with it and just kind of prove it to yourself that these two are really the same thing. So our third component here, this F of lambda, F is for flux, and this is the intensity of the light. The flux of photons. So flux is sort of an unfamiliar term for most of us unless we've taken some engineering classes or something like that. And so it's helpful to maybe think about a tube. And you could think about maybe a hose with water passing through it. And the flux looks at whatever the cross-section area is, and then how much water is going through it, or how much whatever is going through it in a certain period of time. And that's how much the flux is. So our units for light are going to be photons per centimeter squared second, right? So the second gets us at a rate, and then the photons get us at the material we're talking about, and the centimeters squared is that cross-sectional area that we're talking about here. You know, we could have a trickle of water coming through our hose. We could have a big fire hose that's turned up high, right? So we have lots of different options. So if we think about how this is going to affect, how, if we're looking at sunlight as our environmental most important source of light energy, right? Then the flux is going to depend on the wavelength. It's going to depend on the altitude, how high up above the surface of the Earth you are. It's going to depend on where you are on the Earth. We'll just say the latitude. And then the position of the sun, so what time of day it is. And the season, since that also affects where the sun is in the sky and how intense. And all of these factors are important. And the good news is there are tables of all of these values. Okay, so let's go ahead and try a sample calculation of the photolysis rate constant, Kp. So we're going to look at the reaction of nitrogen dioxide gas. This is a brownish gas that's associated with smog. So if you've ever seen smog, often in a winter afternoon, then that brownish haze, that is actually nitrogen dioxide gas. It's not just dust in the air. You can also have some dust, but this is one of the important factors. So we're going to calculate this photolysis constant at 298 Kelvin. Nitrogen dioxide can be broken down into highly reactive nitric oxide and oxygen radicals. And so let's go ahead and calculate this at 298 Kelvin at noon on this at sea level. And there's a table in the book. So go ahead and take a minute and check that calculation. So this is a table. The table is on page 85. It's in chapter 3. So go ahead and take a minute and calculate out those values. I'm going to write out the first one, and then you go ahead and write out the rest and check that you get the same calculation. So the other detail for this problem is if we look up a nitrogen dioxide absorbance spectrum, since it is visible, it makes a brownish gas. We know that it must absorb in the visible spectrum, but all we really need to know is what is the wavelength required to break this nitrogen dioxide bond. And it turns out that that wavelength is at less than 420 nanometers. And so we don't need to look at any of its visible wavelengths because those aren't going to be responsible for this reaction, and so it's not going to result in any reaction occurring, right? So we're just looking below 420 nanometers, and then the table stops at 300 nanometers, and that's because wavelengths less than 300 nanometers are not present at ground level much. Okay, so our first calculation, if we look at that table, for the 300 to 320 nanometer range, we're going to multiply all those bits together. So the first Kp for this, just part 1, I guess, is going to be a phi value of 1, molar absorptivity of 1.9 times 10 to the minus 9, and then a flux of 0.6 times 10 to the 14. We multiply all of those together, and we get 0.1 times 10 to the minus 4 per second. So this may look like a pretty small number, but we actually have this reaction happening relatively quickly. So how do we figure out photolysis lifetimes? How long do we reasonably expect molecules of this kind to persist? So if we remember our rate constant, we would write that the reaction rate is equal to the photolysis constant times the concentration of NO2. And this is the change in the NO2 with time. I'm going to refer you again to the kinetics review section. And so I'm just going to quickly remind you that when we have first order kinetics, the lifetime just depends on this K value. So we can look into half-life as a reminder. And what we find is that the characteristic lifetime for a first order reaction is just 1 over K. So our characteristic lifetime is going to be 1 over, we actually haven't calculated the whole thing, right? Okay, this was just for our first section. I guess it's time for us to pause for a minute here and go and calculate the rest. So go ahead and pause and calculate the rest of our K values, and we'll get this Kp for that entire table from 300 to 420 nanometers. All right, so coming back, hopefully you confirmed that the sum of all of those values, we get a 0.0027 inverse seconds here. So now we can calculate the characteristic lifetime, which is just 1 over that number. And if you do that work, you'll get about 370 seconds, which is 6.17 minutes. Okay, so this is not a terribly long period of time. Nitrogen dioxide doesn't persist in the atmosphere all that long. And I want to also circle back around to this one little piece where we talked about how wavelengths below 320 nanometers are not really present at the ground very much. This is the spectrum, as you can see, of solar radiation at Earth. And what I'm trying to show you here is that we have two different curves. So, well, three different curves really. This black continuous line is a theoretical absorption spectrum. But what I want you to do is look at here at the yellow and at the red. So this yellow, this is the sunlight that is actually incident at the top of the atmosphere. And you can see that for the most part, the most abundant wavelengths here are in the visible, but we have a lot of longer wavelengths. This is all infrared and further out toward microwaves. And then here in the dotted lines, this is our visible range, and we have a bunch of shorter wavelength, some ultraviolet, but tailing off right around 250 wavelength or 250 nanometers. And as you can see from the difference between the yellow curve and the red curve, this is 500 nanometers, so this is pretty close to about 300 nanometers. There's not a lot below 300 nanometers that makes it to the Earth's surface. Most of it, as this little label implies, is screened out by the ozone. So more on that later. Okay, so coming back into our photolysis big idea, we have looked at some photolysis lifetimes, and I want to just kind of point out that photochemistry, or chemical reactions that are induced by light, is really responsible for all of the important chemistry that's happening in our atmosphere, and a lot of it that's happening other places as well. And a lot of the ones that are doing the photochemistry, a lot of the molecules or fragments that are doing the chemistry are going to be these highly reactive oxidizing species. So you might call these oxidants, oxidizers, or oxidizing agents. These are going to scavenge electrons from other more stable molecules that are present in the atmosphere. And a lot of what they do here is kind of clean up the atmosphere. If you need a little reminder on oxidation and on oxidizing agents, then I'm going to refer you to the redox foundational video if you need to kind of refresh up on that one. So some of our most important oxidizers here, this oxidant, the hydroxyl radical, not the hydroxide ion, but the hydroxyl radical, is the most important radical and oxidant in our atmosphere. And it is sort of our atmosphere cleaning agent. And it cleans the atmosphere because it reacts with these other molecules that are around and breaks them down, hopefully into something that is more benign. Okay? So our most important source of the hydroxyl radical is from the photolysis of ozone. And we're going to talk more about photolysis of ozone here as we go on, but this is just our first introduction to it. So when we photolyze ozone, it is in the gas form. It remains in the gas form. It turns into oxygen, and then it turns into this excited oxygen here. So this is a special notation. This 1D, this is a 1 superscript. It's not a like a hyphen or something. This is called Singlet D. Today I can't talk and write at the same time. Come on, eraser. Nope, it does not want to erase. Singlet D is how we would pronounce this. Okay, so I don't want you to get tied up with wondering about this notation, so I'm just going to take a moment and show you what is meant by this singlet D. What I have here is the ground state, the first excited state, and then another excited state of that oxygen atom. So I know this popped right out of nowhere. Let's kind of review a tiny bit and make sure we know where it came from. So oxygen, remember, if we go back in our heads to Gen Chem, we think about the electron configuration of the oxygen. And we remember it has 1s2, 2s2, 2p4 as its electron configuration. So this looks like the 2p orbital here, and we just didn't draw in the 2s or the 1s orbitals here. And this is the case. And the reason that we didn't bother drawing in those additional electrons is that it is the valence or highest level electrons that are the ones that get involved in chemical reactions and in making bonds. So these are our valence electrons, and they are available for bonds and reactions. All right, so this one over here is ground state. As we can see, our 2p4, 1, 2, 3, 4, and this unpairing of these two valence electrons is what we are told is the most stable configuration, and that's true. And so this gets labeled the 3p or triplet p state. You don't need to know why these are P, D, and S. This is just not part of our class. But it's a triplet because there are two unpaired spins, and remember that each one of these has a spin of +1/2, and that if we put this in a magnetic field, because we have two unpaired spins, we actually have 3 different ways for the spins to align in a magnetic field. They could align together, they could align opposite, and they could align together pointed down. So this is what a triplet state is like. So this next this is our excited state that we were talking about up here, the singlet D excited state. And you can see that these two electrons are paired up. That means that our spin +1/2 and -1/2 cancel each other out, and there's only one way for this spin to be, and even in a magnetic field, they can't switch spins because they are paired up. So this is the same thing in our singlet S state here as this other excited state, because these two spins have to stay unpaired and they have to stay opposite. We only have that one option, so it's a singlet state as well. Anyhow, you don't have to know very much about these. I just want, when we say singlet D, I want you not to freak out, but to say, it's an excited state of oxygen. And that's about as far as I need it to go. But I wanted to explain it so that you wouldn't have to feel like you needed to look it up later. Okay, so our hydroxide, we only got halfway through that, right? All right, I'm going to make this a little cleaner. We're going to get back to photolysis of ozone, and then we didn't even make the hydroxyl radical yet. So let's go ahead and do that as our second part. All right, so there's our singlet D oxygen. This is step 1. And then in step 2, that singlet D oxygen reacts with some water in the atmosphere, and it makes 2 hydroxyl radicals. And so you can imagine that, especially in the stratosphere, there's quite a bit of ozone present, but even at ground level, there tends to be some ozone present. This reaction can only happen below 320 nanometers though. So most of this is happening up in the stratosphere, and we're producing hydroxyl radicals because there is going to be enough water vapor around that those singlet deoxygens will have some if it becomes a possibility. So we'll produce some hydroxyl radicals. These guys will then react with other stuff and break it down. So this is our most common method of producing the hydroxyl. We also have the hydrolysis, the photolysis of nitrous acid. This is more of a ground level reaction. And this reaction makes the hydroxyl and nitric oxide. Both of these are pretty reactive. So this happens at below 380 nanometers. So 380 nanometers is just shy of violet. In fact, some people probably can still see it. And so it's pretty easy to break down this nitrous oxide when it's present. All right, so the interesting thing about our concentrations of hydroxyl radical in the atmosphere is that these stay pretty consistent even though they are breaking down a lot. They are also being regenerated a lot. And it's going to be around 10 to the 6 molecules per milliliter, which sounds like a lot until we think about how small molecules are. So anyway, all right, so I'm going to pause now. We're going to have some homework problems to work on in a bit, but I'm going to be producing some more videos before I post another one. So stay tuned.